in the previous lecture, we talked about logic, propositions, and the connected operators, and we talked about and, or, if then, and also if and only if. We also talked about negation. And we explained that if two propositional logics to be equivalent, so they must have the same in the same column in the truth table. We explained truth table as well. We now have this property. We also talked about some properties of logic. We talked about this. We have only these two propositions. We have this proposition, which is absorption. We say if we have two propositions, P and Q, then we say P and P or Q, and also P or P or Q, P and Q, these two are equivalent. These two are equivalent. Here we have only two variables. Since we have two variables, so we must have 2 to the power 2 statements. Yeah, we have P and Q. We have only two variables. 2 to the power 2 is 4. That means we must have 4 variables. How do you write down there? For the first proposition, for P, we write down true, true, then false, false. And for Q, we write down as true, false, true, false. And then we are going to show that P and P or Q is equivalent to P or P and Q. We are going to show that these two are equivalent. It's easier if we expand more. Okay, that means if we first find P or Q, then we combine this with P by AND. If we connect them by AND, then it's easier to get the result. Look, first let's find P or Q. For P or Q, what we get? We say if only one of them is true, so the result is true. So they are gonna wait for the electricity. So do you have any question about these two? We talked about this on the whiteboard. Now we have some exercises. These are for yourselves. The last part of chapter 1 is quantifiers and proof techniques. Here we talk about quantifiers and also proof techniques. In proof techniques, we are going to talk about 3 types of proof techniques. We have 3 methods for proving theorems. For quantifiers, here we say if in a proposition you have variables, that means that's a quantifier. If includes variables, we say that's a quantifier. As you see here, here we have this example. This is, we say P of X is a proposition. We say it is X is greater than 3. X is greater than 3. In the proposition, X is greater than 3, we don't know X is greater or not. So here we have variables in the statement. In the proposition, we have variable. And this is called quantifier. For example, Q of XY. Q of XY, in this proposition, we have 2 variables, which are X and Y. We have X and Y. We say X equals Y plus 3. And also R of XYZ. It's also a proposition with 3 variables, 3 unknowns. We have X plus Y equals Z. These are quantifiers. Okay. If we have variables in the propositions, we say that is a quantifier. Look, we say X squared plus 4X is an odd integer. It's an odd integer. Here, the domain is given. It says the domain of this course is set of positive numbers. A set of positive numbers. This is a quantifier. It's just to know that what's just to describing quantifier. Here in the proposition we have a noun. We have x, which is a noun, and here we say this is a quantifier. And in the second one we have x squared minus x minus 6 equals 0. This equals 0. It says the domain of this course is the set of real numbers. The domain of this course is the set of real numbers. This is a quantifier also, because in the proposition we have variables. It says the university rated as richest university in Malaysia. The domain of this course is set of research university in Malaysia. Okay, one of the universities, we don't know which one. It says the university rated as research university in Malaysia. So the domain is the set of all research university in Malaysia. Here we have also a noun. We don't know which university is that. So that's why here it means we have variables. So it's quantifier also. Here we have a predicate. We say a predicate becomes a proposition if the variable or variables contain these two: assigned specific value or values or quantified. Look, here we have some examples. We say P of x is a proposition or a statement. It says x is greater than 3. X is greater than 3. So what are the truth values of P of 4 and P of 2? Here we say P of x is x greater than 3. So if you replace x by 4, if you have P of 4, how about this one? We can say 4, we just replace x by 4. 4 greater than 3. Is it true? Yes, so this is true. How about P of 2? P of 2. It's 2 greater than 3. Is it true? No, it's false. It's about the truth values of that quantifier. And here we have Q of xy equals. This is a statement which x equals y plus 3. This is a quantifier. Okay. It says what are the truth values of Q of 1 and 2, and also Q of 3 and 0. That means here we should replace x by the first number and y by the second one. We have, let me clean this. Here you have Q of xy. We say this is a proportion, and it is x equals y plus 3. What are the truth values of Q of 1 and 2? That means here, as you see, the first one is x and the second is y. That means we are going to replace x by 1 and y by 2 in the statement. If both sides are equal, we say that's true. If not, we say that's false. Let's do the first one. Q of 1 and 2. We say 1 equals 2 plus 3. Is it? We just replace x by 1 and y by 2. And we get 1 equals 2 plus 3. So 1 equals 5. Is it true? No. So this one is false. Q of 1 and 2 is false. And then Q of 3 and 0. Q of 3 and 0. We say it equals 3 equals 0 plus 3. That means 3 equals 3. Is it true? Yes. So this is true. That's how to find the truth values of a quantifier. Okay. We are going to choose only the numbers which we get true for the statement. And you have two types of quantifiers, which are universal quantifier and also existential quantifier. For universal, we use for all, if it's true for all elements in the domain, then it's universal quantifier. But if it's true for at least, I mean, for some of the elements in the domain, we use that exists, okay? For one or more, not for all elements. If it's not true for all elements, we use the existential quantifier. For the universal quantifier, we say for every x in the domain, the statement must true. The statement must true for all elements in the domain. We say symbol, this symbol, we use this symbol for universal quantifier, and it means for every, and it reads as for all or for any. That means for all x in the domain must the proposition must a of x, okay? We must have a of x. That means a of x must true. Look, universal quantifier, we say for all x, a of x must true. Let's take an example. Look, if this, we say it's true, if for every x in the domain, the statement is true. And it's false if at least we have one element in the domain such that the statement is not true. If we have only one element, which shows that the statement is not true, we say the quantifier is not true at that point. Look, it's not universal quantifier. You can see that here. We say for all x is greater than x squared is greater than or equal to 0. Look, this is the statement. This is the proposition. Our proposition is x squared is greater than or equal to 0. And x belongs to the real numbers. X belongs to the real numbers. That means for all elements in the real number, if we square them, we must get a number which is 0 or bigger than 0. We must not get negative values by squaring the real numbers. ليرة هرج ماري ور بقرم دو جايب كم لبريتو عن كجوتا أيتها وشي بموجة ونيا أي صفر ور بقرين صفر كاتا كواتا ليرة لهن الخيور بقرم ناوج شمال راسك أنا دو جايب كين يا صفرة يا قولت الصفر. Okay, so for all elements in the real number, x squared is greater than or equal to 0. So that's true for all elements in the real number. That's true. There is no any real number such that if we square them, if we square it, and it's less than 0, there is no real number. Even if, let's take a negative value. Let's say -2. -2 squared is what? It's 4. It becomes positive. It's greater than 0. 0 squared is 0 equals 0. That means these are greater than or equal to 0. All of them, all the results are greater than or equal to 0. That means we never get a squared number which is less than 0. Okay, so this is the universal quantifier. And we say it's true for every x in the real number. As you see, this statement is true because every real number x is true that square is positive or 0. Here you have another example. We say let the universally quantified statement is for all x squared is less than or equal to 9. Here, the domain is 1, 2, 3, 4. We only can pick points from B. We cannot pick any other point, any other value. That means you only can replace x by the values which are in B, in the domain. But in the previous example, our domain is the set of real numbers. That's the set of real numbers. But here, our domain is only 1, 2, 3, and 4. As this statement satisfies these all, let's check. For 1, we say 1 squared is 1, which is less than or equal to 9, of course. 2 squared is 4, which is less than or equal to 9. 3 squared is 9, which is less than or equal to 9. 4 squared is 16. It's not less than or equal to 9. It's greater than 9. Okay, so this is at this value, the statement is not true. The statement is not true. So that's why we say the statement is false. We say it's false. We don't say it's in only that point is not true. We say the statement is false. Okay, this statement is false. Why? Because if you replace x by 4, we get 16, which doesn't satisfy this inequality. Okay? Do you get that? دير على أجل هاي يغنر خبي باسا داني نكات يصل الستمنت كفالصة. Okay? لأن كم نخلق معها شوال ما هيك باسا داينا بس يصل الستمنت كفالصة. Here we say if our domain is not small, is too large, let's say. If the domain is too large, okay, and we don't know if there is if there's a point in the domain which doesn't satisfy the proposition or not. Here, for the big domains, it's easier to use existential quantifier. We're gonna just, pick one or more points. That's enough. We don't need to try all the points in the domain. Here we say for the existential quantifier, we say if there is at least one element in the domain which satisfy the proposition, we say that's true. If there is only one point in the domain which satisfy the proposition, we say that's true. Here, there exists x, ax. That means here, we say if there is at least one point in the domain which satisfy the proposition, here a of x is the proposition. If satisfy a of x means the statement is true or the proposition is true. Here we use this symbol for existential proposition. Here we use this for there exists. It means there exists. It's there exists. You say there exists x, a of x. If there's at least one point in the domain, the statement is true. We say the proposition is true. Look, here we say there exists x, a of x. That means if we can find at least one x in the domain, that makes a of x is true. Okay, we say the statement is true also. And we say it's false if for every x in the domain, the proposition is false. I mean, a of x is false. You just need to find only one point in the domain which makes a of x true. Look, here we let the existentially quantified statement is there exists x. X over x squared plus 1 equals 2 over 5. What's the domain? Let's check. We say the domain is the set of real numbers. That means here, if you could find only one value in the real numbers which satisfy this, we say the statement is true. We say the statement is true. If you could find at least 1 point in the real number, such that we get x over x squared plus 1 equals 2 over 5, means the statement is true. Let's check. Here we have x over x squared plus 1. But شجمارك x داب بنيم وقت شيل جي x داب بنيم بوي كدولة سبينجم دسكت. Yes. Look, if we replace x by 2, in the denominator we get 2 squared is 4 plus 1, and we get 2 over 5. Is this equal to the right hand side? Yes. That means we could find at least one element in the domain to satisfy the proposition. That makes the proposition true. So this proposition is true when x is to be 2. So the statement is true because we could find one element in the real numbers, which makes the statement true. That's all. Okay. That's for the existential quantifier. Look, here if x to be 2, we get 2 over 5, which is the right hand side. That means the statement is true. Yes. Sorry. Yes. After this example, we're going to take a break for 10. Okay. So if you have no questions about this example or about what we talked about, we are going to take a break for 10 minutes. Okay. So we talked about this example. It was about existential quantifier. And now we have negation of quantifiers. Negation of quantifiers. We say the negation of universal is existential and vice versa. Okay. The negation of universal is existential, and also the negation of existential is universal. We say the negation of for all x p of x, for all x p of x. Here the negation of for all x, the negation of for all x is p of x, is there exists x, and also the negation of there exists x is for all x. Okay. Here we have negation of for all x p of x. This negation is for this and the statement also. It's for both. It's for all and the statement also. When you give it to this for all, it becomes there exists. And if you give it to the statement, we get the negation of the statement. So the negation of for all x p of x is there exists x negation p of x. You get that? And also, if we have the negation of there exists x p of x, so this negation is for there exists x and for the statement also. When you give a negative negation to a statement, we get the negation of the statement. So here we get the negation of there exists is for all, and negation of p of x is negation p of x. We just leave it like that. So this is the negation of for all x p of x and also for there exists x p of x. Here we have some examples. We say let p of x equals x. Let p of x equals x. Is taking discrete structure course with the domain of this course the set of all students. So here we say p of x is the set of all those students who are taking discrete structure. Okay, p of x equals x. Here is the set of all those students which are taking discrete structure. Here we say for all x p of x, how to express this? We say all students, as it says for all x, that means all students are taking discrete structure course. All students are taking discrete structure course. Since you have for all x, x is the set of all students, okay? We say for all x p of x, that means all students are taking discrete structure course. Here we have there exists x. We say there is or there are some students who are taking discrete structure course. So here, let me plug this to here. Okay. We have for all x negation p of x. That means for all x means all students. For all x means all students. Negation p of x means are not taking discrete structure course. Taking discrete structure course means p of x. And the negation of p of x means are not taking discrete structure course. And here we have there exists x negation p of x. Here it means there are some students who are not taking discrete structure course. If you write down this in words, it becomes there are some students who are not taking discrete structure course. And these are examples about negation of universal and existential quantifiers. Now we have the last topic in this chapter, which is proof techniques. Proof techniques, here we just talk about 3 techniques of proofs, which are direct, indirect. In the indirect one, and also we have proving by contradiction. We have these 3 types of proofs that we talk about here. We say the mathematical system consists of these axioms, definitions, theorems, undefined terms. These all are in the mathematical systems. Okay. And theorems, it can be stated as follows. We say as facts, as implications, as by implications. We can state the theorems like this. Here, an argument that establishes the truth of the theorem, of a theorem, is called proof. Proof وات سلماندني أو إشي كهمان. Theorem بمعنى بيردوزيت. Proof بمعنى سلماندني أو إشي كهمان. أو سلماني كمان بيوزي proof. اشتكى بروفينا كأكاد أو بيشانيا كثير مكان راستا بيوزي proof. Now we have proof techniques. As I said, we have three types of proofs. We have proof techniques. Here we are going to talk about these 3 techniques of proofs. The first one is direct proof, the second is indirect, and the third one is proving by contradiction. We are going to talk about these 3, and here we have an example for each of these 3 techniques, and that's all in this chapter. First, direct proof. For the direct proof, in the theorem, we are gonna give some hypothesis. Here, you can use these hypotheses to prove the required part. Here, let's say P of x1, x2, x3, up to xn. If this is given and it says this is true, if it's true, here, the required is to prove that Q of x1, x2, x3, up to xn is true. Proof we are going to prove this one. By using this given, we are going to prove this one. Okay, for example, here we have given, it says, if x is odd, so it's odd. We just deal with x as an odd number. Then x squared is odd. So you must prove that x squared is odd. Okay, you say if p, then q. That means if this is true, we let that's true. And we prove that this is true also. Okay, that's an example, and we will prove that later on. But let's talk about this first. Here, procedure of the direct proof. What we do, we let D is the domain of the discourse. That's okay, and we show that the statement for all p of x, then q of x. For all x, p of x, then q of x. That means if p of x is true, we are going to prove that q of x is true also. We let p of x, which is the given, is true. And we are going to prove that q of x, which is the required part, is true also. That means here we just need to prove that q of x is true. As here we have this example. It says for all integer x, if x is odd, that means it's given that x is odd. We need to show that x squared is odd also. Let's take some examples, specific examples here. Let's say if x to be 3 is odd or not. That's odd. Let's take its square. X squared equals 3 squared, which is 9. So that's odd. تاع اجمالي تاع بيت اوادو جاكا شي تاع او كدراو جمالي تاع بيت اما دروا اي سلمينين كدو جاكا شي تاع اوش اسلمين. So if x to be, let's say 5, then x squared is 5 squared, which is 25. Say كأجر ما تاع بيت ايش تاع ما تاع ايش كواتا ليرة على اجر جمالي تاع بيت اوادو جاكا شي تاع بيت. Okay, we are going to prove that if x is odd, then x squared is odd also. Here we have some examples. We have p of x and q of x. P of x is the given one, which is x. P of x is x, is an odd integer. And q of x is the required to prove. It's x squared is an odd integer. That means if p of x, then q of x. That means p of x, then q of x. We must prove this. This is given. We must prove that. Okay? It's given that x is odd. We say if a number is odd, it could be expressed as, let's say, a be an odd number. We say a equals 2n plus 1. It's an odd. It's the definition of odd number. 2n plus 1 is the definition of odd number. Look, because every odd number could be expressed by 2n plus 1. Let's say 5. 5 is 2 times 2 plus 1. 3 equals 2 times 1 plus 1. 25 is 2 times 12 plus 1. We can express all the odd numbers as 2n plus 1. Okay, so it's given that x is an odd number. We let a to be a. Okay, let's say it's a. We say a equals 2n plus 1. A equals 2n plus 1. Let me write down here as x. Okay, I'm going to prove as x because in the example it's given as x, not a. It's given that x is an odd number. That means x is 2n plus 1. Why can I write down this? Because x is an odd number. And we say that all the odd numbers can be expressed as 2n plus 1. Now, we are going to take x squared. We are going to take x squared. It must be odd also. We say x squared equals 2n plus 1 all squared. Is it? We just square both sides. And in the right hand side, we have a bracket which is raised to an exponent. We are going to expand the bracket, and it becomes first one squared. If you have a plus b squared, it equals a squared plus 2ab plus b squared. Is it? We have that. We have that rule. So we are going to expand 2n plus 1 squared by that rule. We get 4n squared plus 4n plus 1. And between these two, we can take 2 or 4 as the common. We can take 4 as the common. It equals, let's take 2. We say 2n squared plus 2n plus 1. We say if we multiply any integer number by 2, we get an even number. Okay? And this is an even number. And plus 1 is an odd number. If we add 1 for any even number, it becomes odd. For example, 24. 24 is an even number. If we add 1 for it, it becomes 25, which is an odd number. So this is even. And that's 1. So the result is odd. It's always an odd number. That means here x squared is an odd number. Thus, x squared is odd number. If x is odd, then x squared is odd also. As you see here, we prove that it's an even number, and altogether it's odd. Okay, so here we prove that if x is odd, then x squared is odd also. And here it's proved by a. It's just replace x by a. A is an odd number, so it equals to n plus 1. It's squared both sides, then expanding the right hand side, and you get this. We let 2n squared plus 2n equals m. We let that. Okay, so you get 2n plus 1. This is also an odd number. That means a squared equals 2n plus 1 is an odd number also. That means a squared is an odd integer. So we say if x is odd, then x squared is odd. We prove this by using direct proof. So in direct proof, we use the given to prove the required part. Okay, directly we get the result. But for the indirect one, we say if you have P then Q, what we do, we are gonna prove negation Q then negation P. That means we check the negation of Q. If we get negation of P, it means this is true. Later, agar one later banumni or begin bashra, lesson numne kajuan. Alachi, ale agar n do just I say odd bit, our n is n chia even. Our n even. Then checking. Ale agar n odd bit, Petron emoreg. I'm a Pia, I'm a Q. Negation emor begin check out. I get n odd, I get n odd bit. Our n do just I say chia even. I get later. Das code kawata I make a plus. Okay. Look here. We have indirect proof. We say P then Q is equivalent to negation Q then negation P. These are equivalent. That means if we prove this one, that means this is true also. Okay? If we prove any of these, it means the other one is true also. Therefore, if P then Q is true, so that's true also. And vice versa also. And conversely. To show that negation P then negation Q is true, we take this and we prove that. We take this one and we prove negation P. If you prove that negation P is true, it means P then Q is true. Okay, here we have an example. It says if n squared plus 3 is odd, then n is even. What we do here, this is P, that's Q. We say we take negation of Q, and we must get negation of P. If from negation Q we get negation of P, it means P then Q is true. That means n squared plus 3 is odd, then n is even. So the given statement is true. That means it's the same as to prove that direct. This is indirect proof. What we do here, we say P is this statement. N squared plus 3 is an odd integer. And Q of n is even integer. N is even integer. What we do, we should take the negation of Q and negation of P. That means, look, P is n squared plus 3 is an odd integer. So negation P is n squared plus 3 is an even number or even integer. It's an, because the negation of odd is even, and again the negation of even is odd. Here n is an even integer, so it's negation of Q is n is odd integer. That's n is an odd integer. Look, negation n, if negation Q of n is true, then we need to prove that negation Q of n is true also. Yeah, we have given P then Q. To prove P then Q, what we do by using indirect proof, we are going to take the negation of Q, then negation of P. If this is given, we are going to prove that negation of P is true. If we prove this, it means the above statement is true. It's the same as that we prove the above one. Look, so what's negation Q? We say n is odd. What's the negation P? We say n squared plus 3 is even. And from this, we could get that. It means the above statement is proved. So n is odd. That means n could be written as 2k plus 1, because we said before that all the odd numbers can be written as 2n plus 1. And here we have k. Instead n, we have k. That means we have 2k plus 1 for n, for some integer k. So n is 2k plus 1. Now, what we do? We should construct this one, n squared plus 3. We must construct that. How? By squaring both sides first. We square both sides. And then we expand the right-hand side, 2k plus 1. It becomes 4k squared plus 4k plus 1. What should we add for both sides? We must add 3 for both sides to get n squared plus 3 in the left-hand side. We must construct n squared plus 3. But we have only n equals 2k plus 1. By squaring both sides, then adding 3 for both sides, what do we get? This is n squared. And if we add 3 for both sides, we get n squared plus 3 equals this plus 3. We just added 3 for both sides. Here we have 1 plus 3 is 4. Okay? 1 plus 3 is 4. That means n squared plus 3 equals 4k squared plus 4k plus 4. And here we can take 2 as the common. We can take 2 as the common between these 3 terms. All of them could be divided by 2. And here we get 2 times 2k squared plus 2k plus 2. If we took 2 as the common, we get 2k squared plus 2k plus 2. Now we have n squared plus 3 equals 2 times 2k squared plus 2k plus 2. Is this an even number? Is this an even number? Yes, that's an even number. Because we have a number, we have a bracket which is multiplied by 2. If you multiply any number by 2, we get an even number. For example, 3, 5, 7. Any of these numbers, if you multiply them by 2, we get an even number. That means n squared plus 3 is an even number. So we took negation q, which n is odd, and we obtained that n squared plus 3 is even. We obtained that n squared plus 3 is even. That means p then q is true. That means if n squared plus 3 is odd, means q is an even number. It's the proof of that theorem or example by using indirect proof. So for the indirect proof, what we do, we are going to take the negation for p then q. We get negation q, then negation p. We just follow the proof. And the last one, the last method, the last technique is proving by contradiction. Proving by contradiction. How do you work for this one? We let the result is not true. We let the result is not true, and we get contradiction. ليه ودعني أنجامك الرازني أو أنجامي داكرا أونية جريمان أونية. Again بشتك بيشواني دراوكي. Again بشتك كبيشواني دراوكي. بيشواني أوي كدراو. Here we have an example. كاتيكالي ليرا كالي again بcontradiction معناه و again بشتك كبيشواني أوي كدراو. Again بشتك أنا راستي ليرا دراوكا ناقنج. Okay. Look. Here, it says prove the following theorem. It's a theorem. There are infinitely many primes. It says there are infinite prime numbers. Do you know what are the primes? أزاخو prime شيء. Prime جمارية كتواني دابجموني هي بس الخويوية. Okay, وكو حوت وكو بينش. بلام no تاتا بلام نايت prime. نابت prime. بو لبلو تواني دابجموني بس السيشن. هالجمالة تنها تواني دابج منه بس الخوي وبس اليكا كيوتي برايم. Okay. This theorem says that there are infinitely many primes. Look. How do we prove this? We say we take its negation. We let there are many primes, not infinite. There is infinite primes. We let there are infinite primes, and we must get a contradiction. Okay? Or we must get something not true. Here, we say assume to the contrary that there are only finite many prime numbers, which are P1, P2 up to Pn. Let we have only finite number of primes. We have only finite number of primes. And we consider we have P1 up to Pn primes. We let Q to be a number, which is either prime or not. It's either prime or not prime. Or not divisible. We say if we divide any of the listed primes, P1, P2, P3, up to Pn. If we divide any of the listed primes Pi into Q, the result is only 1. The remainder is 1. The remainder is 1. It proves that Q is also prime number. Look, if we have a number, and if we divide, let's say Q be a number, and if we divide all the prime numbers, P1 up to Pn, by Q, if the remainder is 1 in the division for all, if the remainder is 1, it means Q is also prime, but Q is not listed above here. So that's contradiction. Why? Because here we have no n primes. We have n plus 1 primes, and for the other one, and so on. So we have infinitely many primes. That means we said if you have finite primes. So here we could find another prime number which is not in that list that you put. It means we must have infinitely many primes. So this contradiction. And Q is a prime number, but not listed above. So Q is a prime number and it's contradiction. Therefore, there are infinitely many primes. And this is by contradiction. To prove by contradiction, we let the statement is not true. Yes, says we have infinitely many primes. And we let that we have finite primes. We have finite primes. And we could find another prime was not listed in the list of primes that you take. It means we have another prime, and so on. We have infinite primes. So there are infinitely many primes. This is the third technique of proof, which is proof by contradiction. And here you have only one exercise for yourselves. So I'll prepare a list of exercises for you